Okay, so what have we been doing? We've been restoring the H bar dependence into all of the formulas that we're working out. And if you remember, we said that the overall power of H bar simply reflects the dimension of the observable we're looking at. So that's not very interesting. What is much more interesting is relative powers of H bar. And that tells us whether something is a classical term or a quantum correction. So that's what makes it interesting. So to specifically look at these relative powers of H bar, I want to introduce one more property of these graphs. So I want to introduce the integer L, and L is the number of loops in the diagram, okay? And the number of loops is something that's going to start to make a bit of an appearance from now on. Okay, so let's just work out the number of loops for the two diagrams that we've been looking at. Well, if we look at this first diagram, you can see there's a loop at the top there, and there's a loop at the bottom there. So there's the two independent loops. For this diagram over here, there's one loop there, one loop there, a loop at the top, and a loop at the bottom. So for this diagram, the number of loops is 2, and for this diagram, the number of loops is 4. If this is not crystal clear to you, don't worry. We're going to be using loops from now on for a lot of different things. You're going to get a lot of practice with working with loops. Okay, I'm going to quote a formula now that I am going to prove later in the course. Okay, for now, I'm just going to quote it. We'll prove it actually when we study renormalization, but for now, I just want to use it. So the number of loops is actually equal to the number of internal lines minus the number of vertices minus 1. And I can also write that as internal lines minus the number of vertices plus 1. So I get a nice formula that tells me that the number of internal lines minus the number of vertices is equal to the number of loops minus 1. Now, why is this interesting? Well, look back at the power of H bar that we got. What you can see is one of the quantities that appears is I minus V. So using the formula that I've just written down, we can also write the power of H bar as H bar to the E times plus the number of loops minus 1. Okay, and why is this an interesting formula? Well, it certainly is an interesting formula. Why is it interesting? It's because E minus 1 is some fixed integer for a correlator. So if you pick a correlator, you're calculating maybe phi to the power of k. Well, in that case, E would simply be equal to k. So all of the Feynman diagrams that you draw would have exactly the same value for E minus 1. The only thing that changes between the different diagrams is the number of loops, L. So what we learn is L tells us about the relative powers of H bar. Okay, so that's why it's so interesting. We are interested in the relative powers of H bar, and that's completely coded into the number of loops that appears in the Feynman diagram. Okay, let's just check this formula that we derived for the number that I quoted for the number of loops. So here for this diagram, for this first diagram, if we take the number of internal lines, that's 3. If we subtract the number of vertices, that's 2. And if we add 1, well, we get 2. And that is indeed the number of loops. For the second diagram, the number of internal lines is 7, minus the number of vertices, which is 4, plus 1. Well, 7 minus 4 is 3, plus 1 is 4. So we also got the number of loops over there correct. Good. Okay, so now I would like to draw a couple of different diagrams. So let's draw something for a 2-point function. Okay, so we're studying phi squared. Let me move that over and we'll actually write down that this is phi squared. Let's move that over. Good. So we are studying phi squared correlator. What does that mean? You draw two dots on your page, and the first Feynman diagram would be a line. I'm being a little sloppy. We should say where each field lives and label the external points. I'm only interested in the powers of H bar now, so I'm not going to bother to do that sort of labeling. And then this is one of the corrections we could have at order G. Then at order G squared, for example, we would have things like this. And there's another one. And there's another one. Now, this first diagram has no loops. All of these diagrams have E is equal to 2. So for this particular correlator, H bar to the E minus 1 plus L is just H bar to the 1 plus L. So this first diagram is power H bar. The second diagram is power H bar squared because there's one loop. 1 plus 1 is 2. All of these third diagrams are the power of H bar. 2 loops plus 1 is 3. So those are all H bar cubed. Now we said the first power of H bar we don't really care about. So this first term over here, forget the H bar, don't worry about that. That would be what we would call the classical contribution. This term, this H bar squared term, it's an H bar down from the leading term. This is the first quantum correction, okay? And then this term with 2 loops would be the second quantum correction. And the term with L loops would be the Lth quantum correction. Okay, let me try to hammer this point home with a very specific example. Let's imagine you had 2 electrons that were propagating along. So we haven't studied the Feynman rules for this theory, but I'm telling you that we've got lines for electrons, and those are straight lines, and we've also got wavy lines for the photon. If you were to evaluate this Feynman diagram, the physics of this diagram could be explained by the Coulomb potential. That's the physics that you are probing, and this is entirely classical. If you added a loop, so for example, one diagram you could add is the photon that is exchanged between these 2 electrons. On its passage after leaving the first electron, we have a pair creation of a positron and an electron. They then later annihilate to produce a photon that hits the second electron. This would be a quantum correction to Coulomb, to the Coulomb potential. So you could calculate an H bar correction to the Coulomb potential. What do you think the H bar squared correction to the Coulomb potential would be? Well, here's one diagram that would contribute to it. You'd need to add up all of the diagrams that have got 2 loops in them. And this then would be the second quantum correction to the Coulomb potential. An expansion in H bar is an eminently reasonable thing to do. You start off with a classical term, and then you start off adding corrections of size H bar, then H bar squared, then H bar cubed. It's a very physical expansion to do. What we just argued here is that the power of H bar is related to the number of loops. So an expansion in H bar is the same as an expansion in the number of loops. You would start with the tree diagram, so no loops. Those correspond to the classical contribution. All of the terms with a single loop would be the first H bar correction. Terms with 2 loops would be the second H bar correction, and so on. It's a super physical expansion because you're expanding in powers of H bar, which is something we know how to interpret and something that makes sense. And once again, shouldn't surprise you, it also corresponds to an expansion using some sort of a property of the graphs that we are summing. Great. So that's all I wanted to discuss for this chapter. We'll just take a look at a few comments for the exercises.